So now we've added 4 new chemical reactions to our chemical reaction repertoire or toolbox. Let's apply those to some multi-step synthesis problems. So here I have a tertiary alkyl halide where my bromine is attached to this tertiary carbon. In my product, I have eliminated that bromine and I have a hydroxyl group down here. That implies I need a multi-step process. So somehow I want to make those 2 carbons reactive so I can get rid of the bromine and add a hydroxy group there. One way to do that is to go through an alkene. So if I look at a retrosynthesis analysis, if I could eliminate the bromine to form an alkene, then I could do an addition reaction across that double bond to form the hydroxy group. I just need to pick my reagents just right. So let's do that. Here I have my alkyl halide. It's tertiary. I react that with a very strong base, and it's a small one, so I do an elimination reaction. And I'm going to do this based on Zaitsev's rule to form the most substituted alkene. And at that point, I just need to do an addition reaction, and I need to do it so that I can actually have this anti-Markovnikov addition, adding the H to the most substituted and the OH to the least substituted, and I need to do that with my boron hydration chemistry. So I take my substituted boron compound and tetrahydrofuran, follow that up with hydrogen peroxide to form my final product. Notice I'm still going to get 2 different stereoisomers here, so I still need to separate those 2 products by some synthetic method. How about this chemical reaction? I notice here I have 1, 2, 3, 4 carbons. I have 1, 2, 3, 4 carbons, so I don't have to add any carbons. I've gone from a primary alkyl halide to a ketone. And so these 2 carbons here, I need to do some chemical reaction to these 2 carbons to move the functional group from the N carbon over to the second carbon. And again, alkenes would be a good way to do that. And so let's start off. Here is my alkyl halide. I know I can do an elimination reaction to form an alkene. I can then do an addition reaction at that to form a dihalide, a vicinal dihalide, and then I could do a double elimination reaction to make an alkyne, and then I could do an addition reaction of water, a hydration reaction to form the enol, which would tautomerize up to the ketone. Pretty complicated. Let's look at how that all works. And so in this case, I take a primary alkyl halide and I use the hindered base, so dibutyl nitride here, so I know I get the elimination product. I react that with bromine using methylene chloride as a solvent, so I form the vicinal dihalide. I then react that with very strong base to do a double elimination to form the alkyne, and then I do the hydration reaction in the presence of mercury so that I selectively form the ketone instead of the aldehyde, my target molecule. A lot of steps here and a lot of thought went into doing this. It's easy when you just show it on paper. Here's an interesting one. I have an alkyl halide that's also an alkene. I have 1, 2, 3, 5 carbons. Here I have 1, 2, 3, 4, 5 carbons. I know about substitution reactions, so I need something to attack, maybe is my thought right now, to attack that carbon to do a substitution reaction. Maybe I could make this side of the molecule nucleophilic so that it could attack that carbon in a ring. Following that strategy, I take my alkene, I do a hydration reaction to form a hydroxide. This has a lone pair of electrons, which then could internally cyclize by attacking that carbon in a substitution reaction to form this cyclic molecule. And here are the reagents that I chose. I literally chose sulfuric acid and water to do a hydration reaction, and this is under Markovnikov addition, so I add the hydrogen to the least substituted. I add the OH to the most substituted to form my alcohol. Then I use a strong base to actually deprotonate that hydroxyl group to make it nucleophilic. So I literally formed an alkoxide, which then can attack that bromine there. And I get my product. Let's do one more. Here I have a cyclic alkene. Here I have a cyano compound. Somehow I had to actually attack that. So let's turn this into an alkyl halide, and then let's do a substitution reaction. So from a retrosynthesis standpoint, I start from an alkene, I make it into alkyl halide, I do an SN2 reaction to form the cyano compound. The chemical reagents that I chose for that are simple HBr. I react that alkene in an addition reaction to add hydrogen to one of the carbons and bromine to the other. And then I react that with sodium cyanide to actually do an SN2 reaction. I get my product. Now these retrosynthesis or in these multi-step synthesis problems are complicated, and it takes a lot of thinking, and there are many, many different ways that you could do a synthesis like that. As we build onto our chemical reaction repertoire, we'll come up with alternative ways of making the same compound. And then we're going to go on in the next chapter to talking about alcohols.